All right, let's jump right in. We are absolutely surrounded by incredible machines, everything from our cars to the power plants lighting up our cities. But underneath all that incredible motion, there's this invisible world of pushes, pulls, and twists. Today, we're going to peel back the cover and really get a handle on the hidden engineering that keeps these machines from just, tearing themselves apart.
So, take a look at this. This is a classic 4-bar mechanism. You'd find this kind of linkage in all sorts of things, from engine parts to maybe even your desk lamp. But think about it. When you apply a force to it, how do engineers know for sure that it's actually strong enough? How can they possibly predict the forces flowing through every single one of those pins and links to guarantee it won't just buckle or snap? Well, that's the big question we're going to answer today.
And believe it or not, the answer starts in a pretty surprising place. Before you can even begin to understand how machines move, you first have to master the art of making them stand perfectly still, even when they're under a ton of pressure.
And this right here is the bedrock principle of all mechanical design: static equilibrium. You can think of it like a perfect game of tug-of-war. If every single force pulling in one direction is perfectly canceled out by a force pulling in the opposite direction, well, nothing moves. It's a state of perfect, unshakable balance. For any part of a machine to be stable, it has to be in static equilibrium.
Now, here's how engineers turn that concept into a rock-solid guarantee. These are the golden rules. Basically, they say that for any part to be stable, the sum of all the forces pushing left and right has to be 0, the sum of all the forces pushing up and down has to be 0, and the sum of all the twisting forces, what we call torques, also has to equal 0. If a component checks all 3 of those boxes, it is fundamentally stable. It just will not move, period.
Okay, so we've got the rules, but how in the world do we apply them to a complex machine with all these moving parts? Well, the trick is to not look at the whole thing at once. Instead, we break it down piece by piece, and we make those invisible forces visible. Let's start with the most basic building block you can have. This is a two-force member, which is just a fancy way of saying a part that only has forces acting on it at 2 points. For this piece to be in balance, the logic is super simple. The two forces have to be in a perfect tug-of-war. They've got to be equal in strength, pulling in opposite directions, and they have to act along that imaginary line connecting them. If anything is off, the part would start to move or twist. And this is a brilliant illustration of what happens when we add a third force. For a 3-force member to be in equilibrium, the lines of all 3 forces have to meet at a single point. But here's the real aha moment. If you take those 3 force arrows, those vectors, and you draw them tip to tail, they form a perfect closed triangle. That visual closure, that's the proof that all the forces add up to 0. There's no leftover force pushing the object anywhere. It's perfectly balanced.
So how do engineers do this for every single part, every time? They use their most powerful tool, the free body diagram. The whole idea is to mentally free a single component from the rest of the machine, just isolate it in your mind, and then sketch out all the outside forces that are acting on it.
Let's actually see this in action. We start with the full mechanism on the left. Now, to figure out what's happening on link 4, we just pull it out. We isolate it and draw its free body diagram. By doing that, we can clearly see the known force F pushing on it, the force from link 3, and the force from that pin on the ground. Just like that, we've turned a complicated problem into a simple 3-force member, which we now know exactly how to solve.
Okay, standing still is one thing. We've pretty much got that covered. But machines are built to move, right? To accelerate. And that's where the physics starts to get even more interesting.
Here's the big difference with moving machines. When a part that has mass speeds up, slows down, or changes direction, it fights against that change. We've all felt this, right? It's that feeling that pushes you back into your seat when a car floors it. In engineering, we can actually treat this resistance, this inertia, as a real force that we have to account for in our calculations. And this leads to this wonderfully clever trick called D'Alembert's principle. What it does is it lets engineers solve a really complex motion problem using the simple rules of statics we just talked about. All you do is you calculate the part's inertia, which is just its mass times its acceleration, and you add it to your free body diagram as a sort of imaginary inertia force acting in the opposite direction. And just like magic, your dynamics problem suddenly looks just like a statics problem again. Everything sums to 0. It's a fantastic shortcut. But, calculating all those different accelerations and inertia forces for every single part can get, well, pretty tedious. So, engineers came up with an even more elegant method, a shortcut that kind of bypasses the forces altogether and looks at the problem through the lens of energy.
It's called the principle of virtual work, and it's basically a thought experiment. First, you just imagine the mechanism moves a tiny, tiny virtual amount. Then you figure out the work done by your input forces during that little move. After that, you calculate the work done by the output forces. And for the whole system to be in balance, the total work has to add up to zero. It's really just the law of conservation of energy dressed up in a different outfit.
Here's a perfect example on a slider crank mechanism. We imagine the input crank turns by just a tiny little angle. As a result, that output piston moves a tiny little distance. The principle of virtual work just says that the input work, that's the torque times the little angle, has to be perfectly balanced by the output work, the force from the piston times that little distance. Input work equals output work.
And the absolute beauty of this energy method is that it all boils down to this incredibly clean and powerful equation. It directly connects the input torque on the crank to the output force from the piston, just by using the ratio of their speeds. It's an amazing shortcut for finding forces in a moving system without having to analyze every single component.
So we can analyze forces when machines are standing still and when they're moving. But there is one last piece to this puzzle. A lot of machines, especially something like an internal combustion engine, don't get or deliver energy smoothly. Their power comes in little pulses. So how do engineers tame that jerky rhythm?
Well, the solution is this brilliant piece of engineering, the flywheel. You've probably seen one before. It's that big, heavy, solid disc you often see attached to the end of a crankshaft. And its job is just elegantly simple. It stores and releases energy using its own inertia. I like to think of a flywheel as a kind of mechanical energy piggy bank. In a car engine, you get one big, powerful explosion, the power stroke, that provides a huge burst of energy. The heavy flywheel absorbs all that excess energy, and it speeds up just a little bit. Then it releases that stored rotational energy to push the engine through the other 3 strokes that don't produce power. The result? It smooths out the entire cycle. Now, it is really important not to get a flywheel confused with a governor. They sound kind of similar, but their jobs are totally different. The flywheel smooths out the speed bumps within each and every cycle. The governor, on the other hand, controls the average speed over many cycles by adjusting the fuel when the overall load changes, like when you start driving up a hill. The source material we're using today puts it perfectly. It says, and I'm quoting here, "A flywheel controls the speed variations caused by the fluctuation of the engine turning moment during each cycle. It does not control the speed variations caused by the varying load. One manages the rhythm, the other manages the demand. It's a key difference."
So how much smoothing do you actually need? Well, it depends completely on the machine's job. This table shows something called the coefficient of fluctuation of speed for different machines. Look at the difference. A big rock-crushing machine can be super jerky. It has a coefficient of 0.2. But a direct-drive electrical generator, it has to be incredibly stable, with a coefficient of just 0.002. An engineer uses this number to calculate exactly how big and heavy the flywheel needs to be for that specific job. All right, so let's wrap this all up. We started with static equilibrium, the core idea that all forces have to cancel out for anything to be stable. We learned that free body diagrams are the key tool engineers use to actually see and analyze these forces. For moving systems, we have to add in inertia forces, or we can take that elegant shortcut using virtual work. And finally, we use flywheels as these amazing energy reservoirs to smooth out the natural rhythm of machines that run in cycles. In the end, this invisible engineering is happening all around us, all the time, keeping our world running. So the next time you see a big piece of construction equipment or an old engine at a museum, take a closer look. Now that you can kind of see the world through an engineer's eyes, can you spot the simple 2 force members? Or can you guess where the heavy flywheel might be hiding?